Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the another lecture on linear control systems. So today is a very special lecture for two reasons. First reason is that the topic of this lecture is going to be a bridge between linear control systems and nonlinear control systems. And the second special reason is that with this lecture, my playlist of lectures on linear control systems shall be complete, and now this playlist will comprise of a complete undergraduate course on linear control systems, or sometimes called control systems, that is taught internationally at many universities for electrical engineering department students, or mechanical engineering department students, and aerospace department students as well. So this gives me a lot of pleasure, and I'm looking forward to completing this video already. So without further delay, let's go into what we covered in the last lecture. Last time we discussed the general form of state space and transfer function and conversion of state space from transfer function and differential equation. So here is the summary. This is the standard form of differential equation. You can see the coefficients. The coefficient of the highest derivative of y is always 1. This is the convention in the standard form. Then this is coefficient a1, a2, a3 and up to so on an, and these are the coefficients of the derivatives of the input b0, b1, b2 and up to so on bm. And this, in order to translate this into transfer function, all you have to do is convert the derivatives into the powers of s, and the derivatives of the output go into the denominator with the same coefficients a1, a2 up to so on an, and the derivatives of the input go into the numerator as powers of s, and the coefficients go as with them, like b0 goes into b0 and b1 here become b1 and so on. Similarly, if you convert this into controllable canonical form of state space, you define the state such that x1 state is equal to the output, x2 state is equal to the derivative of the output, and so on. The states are defined in the way of integrator chain, and then the resulting state space becomes something like this. The A matrix is all zeros, but there are ones above the main diagonal, and there the last row has the coefficients of the derivatives of the output in the reverse order with negative sign. The entries in the B matrix are all 0 except the last entry, which is 1. Entries of the C matrix include the coefficients of the derivatives of the input, and there are some zero fillings which are equal. Number of zeros here is equal to n minus m minus 1, so it is 1 less than the difference between n and m. And of course you can convert state space back to transfer function using this matrix multiplication, C into Si minus A inverse B. We already did examples of that in the last lecture. So let's keep going towards the topic of today's lecture. Today I'm going to combine two lectures together, lecture 5 and lecture 6. Lecture 5 is mostly about linear approximation of nonlinear systems without the control, and lecture 6 is about linear approximation of nonlinear systems with control. So I'm going to cover both of them quickly in this video lecture, since video lectures are much shorter compared to the lectures in the classroom, because in the classroom there are some live discussions and question answer sessions and so on. But video lectures have their own advantage, that you can watch the video at your own time, at your own pace. You can watch it as many times as you want, and so on. So motivation for linear approximation of nonlinear systems. Almost every real world system is nonlinear. That's not a very good news for the students who are studying linear control systems in their undergraduate degrees, but most of the engineering tools and methods are linear, and these linear tools work. So if you apply these linear tools on these nonlinear systems, having some linear approximations of nonlinear systems, these linear tools work actually pretty well. So that's the good news for the students who are learning linear control systems in their undergraduate degrees. Then why do these tools work? Because the linear approximation works. So since the linear approximation works, that is why we still have linear control systems as a one of the core courses in multiple engineering domains. And we not only teach linear control systems, but also in industry linear control systems are applied with full confidence, and they work as well. So understanding linear approximation. So before I tell you the formal methods of how you do the linear approximation of nonlinear systems, let me just build a little bit of a foundation, a conceptual foundation. Let us suppose we have a function, nonlinear function of let's say x. This is a nonlinear function. It is nonlinear because it is not a straight line, and also because with this function, if x is the input of a system and f of x is the output of the system, then this input output will not follow superposition principle. That is why it's not linear. But if you pick any operating point, if you pick a value of x, so let me write down so this is x, and this is f of x. Okay, so sorry about this poor handwriting. I don't have a writing pen with me, so I'm just writing using the mouse pad of the laptop. So we pick this point, and at this value of x we want to approximate this function f of x as a linear function. So if you draw a straight line through this point, which has maximum overlap with this function f of x, then this straight line you can see here in the vicinity, this is the point x, and this is the range around the x. So starting from here, let's say this is 0 to here, this point. So within this range, this linear approximation is almost exactly the same as the original nonlinear function f of x. And also if you pick another point, then you can approximate f of x with another linear function. So the linear approximation of f of x is different depending upon the point, the value of x around which you are approximating this function f of x. So this function f of x can be called this point where we are doing the approximation of f of x, this point can be called a critical point, or the operating point, or the point of approximation. And then around this point of approximation there is a small range within which the linearization is accurate approximation of f of x, and outside that range, the range of values of x, outside that range of values of x, the approximation is no longer very good. So for example, for this case, the range is sort of from this value to this value. Within this range, the linear approximation is working very nicely. And also for this case, we have this range. So within this range of the values of x, the linear approximation works very well, and outside this range the linear approximation does not work that well. So these are the concepts. So if you in terms of state space, if you have like a one-dimensional state space system, you have x dot equal f of x, then you decide, first of all you have to decide about the point about which you want to approximate the nonlinear system. Next, you find the slope of the function at the point of interest, like this. So here we have, in order to have maximum overlap of this line with the nonlinear curve, actually the technique to maximize the overlap is to basically make the slope of this line equal to the slope of f of x, which can be calculated by using the derivative of f of x at this point. And then linear approximation is given by x dot equal m times x. So this is the equation of a straight line, but except that the dynamics of the states are now linear function of the state itself. But here notice that in general there will be slope plus y-intercept. So for example, in case of this line, if this point is 0, then this line is okay, its y-intercept is 0. But in this case, the y-intercept of the line will not be 0. So why have we not written the y-intercept here? So there is a particular reason behind that. The new x in the linear approximation is basically a shifted version of the original x. Whenever original x is equal to the value at this point, we take this point to be the new reference for this x in the linear approximation. So this new x is 0 at the point of approximation. Its value is basically the deviation of the original x from the point of linearization. For example, here if this point is x is equal to 1 and this point is so in linear approximation x is equal to 1, the new x will be 0 here, and here the original x will be equal to 2, but the new x will be equal to 1 here. Here the original x will be equal to 0, but the new x will be equal to minus 1 here. So minus 1 means that we have deviation of 1 in the negative side from the point of operation, or from the point of linear approximation. So this is important to understand that we basically redefine or change the reference zero reference of the linear approximation state with respect to the original state. Note that x dot equal to mx plus c would not be a linear approximation. So if we don't change this if we don't change the value of the linear state with respect to the original state, then we would get something like x dot equal mx plus c. X dot equal mx plus c, it looks linear, but actually it does not follow superposition principle because it is actually an affine function. What are affine functions? You can just Google it and you can find, or maybe you have learned it already in your basic mathematics courses. Okay, therefore it is important to redefine the new x in the linear approximation so that the new approximation system or estimated this is the estimation or approximation of this original system. So approximation must be linear and it must satisfy superposition principle, otherwise we could not call it linear approximation. So this was some initial concept, and now we look at some examples which are like this was like one dimensional. Now we are ready to go into more dimensions. So you can imagine this function to be a 2D plane which is nonlinear or folded at different points, and you can approximate a nonlinear or folded plane with a straight plane which looks like a straight flat plate or something. And similarly you can imagine linear approximation in 3 dimensions, 4 dimensions, 5 dimensions, and so on. So a pendulum example, the inverted pendulum or pendulum looks something like this. So pendulum will have a rod and the bob or blob at the end of the rod, and this will usually make an angle theta with the horizontal with the vertical, and the dynamical equations of motion of this pendulum would be something like theta double dot plus theta dot plus sine theta is equal to 0. This is the uncontrolled system. We have not introduced control here. So equilibrium point. So first of all, as we did in the conceptual slide, we always pick a point. So we always pick some point about which we need to do linearization. In control systems, that point is a special point which is called equilibrium point. So we always do linear approximation about the equilibrium point. Why do we do that? Because linear equilibrium point is a special point at which all the dynamics of the system are zero. So zero dynamics make the equilibrium point a special point, because if the initial condition of the system is at the equilibrium point, then the system will stay forever at that point, because rate of change of the variables in the system are zero at the equilibrium point. So whenever I say the word point means some value of theta. In this case, the value, if it is a 2, if I convert this differential equation into state space where there are two states, then the word point will mean a value pair of two states. So if there are two states x1 and x2, if you assign x1 a fixed value and x2 another fixed value, then the pair of these two values, that is a point in the state space. For equilibrium, for the pendulum model, the equilibrium points are the values of theta for which theta dot and theta double dot both are zero. If we put theta double dot and theta dot equal to 0 in this equation, then the values of theta are obtained from this sine theta equal to 0, and whenever sine theta is equal to 0, theta will be either 0 or pi or minus pi or 2 pi or minus 2 pi or 3 pi or minus 3 pi or so on. So in short, theta will belong to the set 0, plus minus n pi, where n is an integer. So these are all the equilibrium points of this pendulum system. Okay. Physically, there are only two distinct equilibrium points, 0 and pi. So every other equilibrium point, for example, 2 pi is equal to 0, 3 pi is equal to pi, 4 pi is equal to 0, 5 pi is equal to pi, minus pi is equal to pi. Physically, if you look at the pendulum physically, if it is at 0 degree angle or 360 degree angle, you cannot tell the difference. So that's why we just consider two equilibrium points if we are dealing with the physical systems, and we are usually dealing with the physical systems as engineers. So if we look at the graph of sine theta from 0 to pi, so sine theta is 0 at 0 and 0 at pi. So the equilibrium point are theta equal to 0 and theta equal to pi. So these are the two equilibrium points, or the value. These are two values of theta at which all the derivatives of theta are 0 in this differential equation. Near theta is equal to 0, sine theta is nearly equal to theta, because if you look at this, if I had to approximate this function with a straight line, this will be a straight line with slope 1. So if the slope is 1, then sine theta is nearly equal to theta, and so near theta equal to pi, this line is coming down with the same slope as it was going up with. So slope is approximately -1. So near theta equal to pi, sine theta is nearly equal to minus theta, and then you can basically convert theta double dot plus theta plus sine theta equal to 0 into theta double dot plus theta dot plus. So you can replace sine theta with plus theta wherever you are close to theta equal to 0, and you can replace sine theta with minus theta whenever theta is close to pi. So these are the two linear approximations of this nonlinear differential equation. So this differential equation is nonlinear because sine term is nonlinear term. This double derivative is a linear term, this single derivative is a linear term, but this is a nonlinear term. So this nonlinear differential equation has two linear approximations depending upon the two equilibrium points. Now we get a little bit more serious, because this way of linearizing is good for pendulum example, but in general, if there is a difficult example, then we may not have this simple approximation of sine theta equal to minus theta and sine theta equal to theta. So what are the 5 steps of calculating linear approximation? So step number 1, write the model of the nonlinear system in the state space form. We did not do this test step number 1 in the previous example of pendulum example, but we will do this in the upcoming example. So for example, if this is theta double dot plus theta dot plus sine theta equal to 0, define x1 state variable to be equal to theta and x2 state variable to be equal to theta dot, and then this implies x1 dot equal x2 and x2 dot equal to minus x2 minus sine of x1. You already know how to convert differential equation into state space, so I don't have to spend more time here. Find the equilibrium points values of the states at which the state dynamics are 0. So for example, x1 dot will be 0 if x2 is 0, and x2 dot will be 0 if x2 minus sine of x1 is 0. Since x2 is already 0 for making x1 dot 0, so we only need sine of x1 to be 0 in order to make x2 dot equal to 0. So sine of x1 will be 0 if x1 is 0 or pi, and hence there will be two equilibrium points. The first equilibrium point will be 0 0, where x1 and x2 both are 0, and the second equilibrium point will be pi 0, where x1 is equal to pi and x2 is equal to 0. And then verify that both of the points x dot will be like x dot is equal to x1 dot and x2 dot simultaneously. So if you put x1 is equal to 0 and x2 is equal to 0, this will ensure that x1 dot and x2 dot both are simultaneously 0. Similarly, if you put x1 equal to pi and x2 is equal to 0, then this will ensure that x1 dot and x2 dot are simultaneously equal to 0. Then we continue. There is a third step. So this third step is the most important step. Actually, this is the equivalent of finding the slope of the function. Remember that in one-dimensional linearization example, we needed to find the slope of the function at the equilibrium point. So we do the same in the higher dimensional examples. So except that in two-dimensional or three or more multi-dimensional examples, the differentiation will be called Jacobian. So Jacobian is the derivative of this function f of x, which is equal to the state dynamics. F of x is x1 dot and x2 dot. Remember that x dot equal to f of x is our notation that we used in the one-dimensional case. So same notation we carry in this case. So f of x has two components. F of x has x1 dot, which is equal to x2, and x2 dot, which is equal to minus x2 minus sine of x1. And then Jacobian will be the derivative of this f of x components with respect to the derivative of the state vector. So how do we calculate the derivative of a vector with respect to another vector? That is the Jacobian. Jacobian is a way of calculating derivative of a vector with respect to another vector. So what we do is the first row of the Jacobian is partial derivative of f1 with respect to partial derivative of x1, and partial derivative of f1 with respect to partial derivative of x2. So these are the first row are the partial derivatives of f1 with respect to all the state variables one by one, and the second row is the partial derivative of the second component of f of x, which is f2, with respect to all the state variables one by one. So this is how you calculate Jacobian. So even if this f has three components and there are three states, then this will be a 3 cross 3 matrix, where the first row will be partial f1 with respect to x1, x2 and x3. Second row would be partial f2 by partial x1, partial f2 by partial x2, partial f2 by partial x3, and the third row would be partial f3 by partial x1, partial f3 by partial x2, partial f3 by partial x3. So anyways, if you calculate the partial derivative of, so this is f1, so this is f1 is equal to x2, so its derivative with respect to x1 will be 0, and its derivative with respect to x2 will be 1, and this is f2 is minus x2 minus sine x1, so its derivative with respect to x1 will be minus cos of x1, and its derivative with respect to x2 will be minus 1. So this will be the Jacobian matrix for the system, which is the step 3 of calculating linear approximation of nonlinear systems. Next, once we have the Jacobian, we have to evaluate the Jacobian at each equilibrium point. So if we evaluate this Jacobian matrix at x1 equal to 0 and x2 equal to 0, then this term has x1. If we put x1 equal to 0, then cos of 0 is 1 and this minus will prevail. So the matrix will become 0 1 minus 1 minus 1, and this is how it is: 0 1 minus 1 minus 1. And if you evaluate the Jacobian at x1 equal to pi and x2 equal to 0, then cos of pi will be minus 1, and the minus before the cos of x1, that will be cancelled out with the minus of the evaluation of cos of x1. So this will be the Jacobian matrix evaluated at the second equilibrium point. So this was step 4 to evaluate the Jacobian at the all of the equilibrium points. And finally, step 5 is to write the state space form of the linear approximation. So at the first equilibrium point, delta x dot is equal to delta x1 dot delta x2 dot times so this is equal to A matrix times the x. So this is x dot equal A into x, where A is the matrix of coefficients. So here I have represented this linear approximation state as delta x instead of x. So remember, this is whenever we do linear approximation, so in the linear approximation, the new states are basically the difference between the original state and the equilibrium point. So in this case, since equilibrium point is 0 0, delta x will be equal to x. At approximation at the second equilibrium point, that will be the second Jacobian evaluation, this Jacobian evaluation times x. So this will be the second linear approximation of the original nonlinear system. So you can see here that with 5 steps of linear approximation, from step number 1 to step number 1 was to write the system in state space. Step number 2, find the equilibrium points. Step number 3, find the Jacobian matrix. Step number 4, evaluate the Jacobian matrix at the equilibrium points. And step number 5 is to write the linear approximation at different equilibrium points in the linear state space form. So this completes the lecture number 5, and we continue on to the lecture number 6 in the same video. The state vector in the linear approximation is the perturbation of the original state vector around the equilibrium point, as we discussed in the one-dimensional example as well. So this is the summary of 5 points of linear approximation. Write the model of the nonlinear system in state space form. Find the equilibrium point values of the states at which all the state dynamics are 0. Find the Jacobian of f of x. Evaluate the Jacobian at each equilibrium point, and write down the state space form of the linear approximations. So notice that there could be multiple linear approximations for a single nonlinear system. In fact, there are as many linear approximation as there are number of equilibrium points. So original nonlinear state space would be something like x dot equal f of x. Linear approximations would look like delta x dot equal A times delta x. In many books, this delta is not written with the linear approximation. The linear approximation is written just like this state space. So x dot equal Ax, where it is understood that in linear approximation, the state variables are the deviation of the original state variable around the equilibrium point. So delta x is the x minus x star, which is the deviation of the original state about the equilibrium point. So now we go into linear approximation of systems with control. So consider a nonlinear system of the following form: x dot equal f of x comma u. So now this nonlinear function is not just a function of state, it's also a function of the control input u, where x is the n-dimensional state vector, u is the m-dimensional input vector, and f is Rn cross Rm, so it's basically a matrix. So it's not a matrix, it's just it is a function of vector x, which is Rn, and vector u, which is Rm, and it generates the vector Rn. So f is of course a vector of Rn, because f is the derivative of this vector. This is the state derivative vector, which is of Rn. Okay. We wish to compute the linear approximation of the above system about u. So the trick in calculating the linear approximation of systems with control is that you assign the control input some equilibrium value. So some value around which you want the control, in linear approximation, control will be 0 at u is equal to u star, and the same thing will work. The control signal will have to have very little deviations about this u is equal to u star. So step 1, write the equations of the system in state space form. The steps are basically the same. There is only a little bit different with the introduction of this control input u. So write the equations of the state space of the system in the state space form. X dot equal f of x comma u, where u could be equal to u star. Then f of x, find the equilibrium points of f of x comma u with u is equal to u star. So this will give you some x star. So there will be one or more equilibrium points. Step 3 is to find the Jacobian. So in this case there will be two Jacobian matrices. One Jacobian matrix will be the same as before, which is the Jacobian will be the derivative of f vector with respect to the state vector, and the new equilibrium point will be the derivative of this f vector with respect to the control vector. So if u is u1, u2, u3, um, so u is m cross 1 vector, then this matrix will be n cross m matrix. So first row will be partial f1 by partial u1, partial f1 by partial u2, up to so on partial f1 by partial um, and similarly the last row will be partial fn by partial u1, partial fn by partial u2, and up to so on partial fn by partial um. And then another thing is to evaluate the Jacobian matrix at x is equal to x star and u is equal to u star. So there could be many equilibrium points, 1, 2, 3, up to so on. So equilibrium points are represented by this superscript j here. The same is used as subscript in the system matrix A. So partial f by partial x evaluated at the equilibrium point values of x and u, that will be the A matrix of the linear approximation, and partial f by partial u evaluated at the equilibrium point values will be the B matrix of the linear approximation. And the linear approximations will be something like x dot equal ax plus bu, which is basically the linear systems form of system with control. Delta x will be of course equal to x minus x star, and delta u will be equal to u minus u star. So this u here will be the deviation of the original u around the equilibrium value of u. So the difference between equilibrium value of x and the equilibrium value of u is that mostly you find x star by satisfying the condition of equilibrium point, and you define u star by yourself, because u is the control input, and control input is something that you apply to the system. So you know better what value of control input would be the operating point value for the linear approximation. So for example, now let us do some mathematical example. Consider the following nonlinear system: y triple dot plus y sine of y double dot plus y dot square plus y is equal to cos of u. This is a single input single output system, and we convert this, we have to find the linear approximation of the above system, and we define u star to be equal to 0, which means that we are willing to apply very small control inputs for the linear approximation. or in general this system will be controlled with u which will have values close to 0. So step 1, for this nonlinear system to be converted into its linear approximations, the step 1 is to write the state space model, define x1 equal to y, x2 is equal to y dot, x3 is equal to y double dot, and then x1 dot will be equal to x2, x2 dot will be equal to x3, and x3 dot will be equal to cos of u star minus x1 minus x2 square. This is derived from this equation, minus sine of x3. Step 2 is to calculate the equilibrium points. If x1 dot is to be 0, then x2 will be 0, and if x2 dot is equal to 0, then x3 will be 0, and if x3 dot is equal to 0, then since x2 and x3 are already considered to be 0 to make x1 dot and x2 is equal to 0, we only need to worry about this x1, and u star is also already we have defined it is 0. So in order for x3 dot to be equal to 0, x1 has to be equal to 1, because cos of 0 will be 1 here. So in order to cancel out this 1, x1 will have to be equal to plus 1. So that will make x3 dot equal to 0. So the equilibrium point is 1 0 0. x1 is equal to 1, x2 is equal to 0, and x3 is equal to 0. That's our equilibrium point for this system. That's the only equilibrium point. So this system has only one equilibrium point, so there will be only one linear approximation. So step 3 of linear approximation, that is to calculate the Jacobian matrices. First Jacobian matrix will be the derivative of this f of x with respect to x. So partial f1 with respect to x1 will be 0, partial f1 with respect to x2 will be 1 because f1 is x2, and partial f1 with respect to x3 will be 0. Similarly, partial f2 with respect to x1 will be 0, partial f2 with respect to x2 will be 0, partial f2 with respect to x3 will be 1. Similarly, partial f3 with respect to x1 will be minus 1, partial f3 with respect to x2 will be minus 2x2, and partial f3 with respect to x3 will be minus cos of x3. Similarly, partial f1 by partial u will be 0 because there is no u in the f1 term. Similarly, partial f2 by partial u will be 0 because there is no u in the f2 term, and partial f3 with respect to partial u will be minus sine of u. So I apologize for toggling between u star and u here. Do not get confused here, because we will get rid of this confusion as soon as we do the step number 4. Technically I should not be writing u star here. This should be just cos of u, because we are going to substitute u equal to u star in step number 4. Now we go into step number 4. Evaluate the Jacobian matrix partial f by partial x at x equal to x star and u equal to u star. So here, where there are no x1, x2, x3 or u, these numbers will remain the same, and where there is x1, x2, x3 or u, we will put their corresponding equilibrium values. So x2 has the equilibrium value of 0, so we will put 0 instead of x2 here, and x3 also has 0 equilibrium point value, so we will put cos of 0 will be 1, so minus cos of 0 will be minus 1. Similarly, partial f by partial u, it has u only here, so equilibrium point value of u is 0, so sine of u star, that will be sine of 0 is 0, so B matrix will be all zeros in this case. So this in this way, step number 5, just write down the corresponding linear system x dot equal ax plus bu, and you can also write y is equal to cx because you have defined x1, x2, x3 in the beginning, so you know what is the relationship between y and the state vectors. So since we defined here since we define x1 is equal to y, so y will be 1 times x1 plus 0 times x2 plus 0 times x3. So in the linear state space form, x dot equal ax plus bu, y is equal to cx. So remember that I have not written down delta x instead of x here, because at this point, by this point I assume that it is clear that in linear approximation the states are deviation of the original states from the equilibrium point. So these states are the deviation of the original states from the equilibrium point, which is 1 0 0. And that is it, and that completes lecture number 5 and lecture number 6 of this course, and this completes the whole course of linear control systems. I will continue posting some additional tutorial videos, for example the control tuning related videos or LQR related videos. Recently one of my book chapters got published, which basically tells you how you can reverse engineer the LQR controller and find the corresponding PID control gains. I will also try to make a video on that book chapter. There are a lot of things I have planned for the future on this YouTube channel. I have a plan that I'll hopefully make it a bigger platform for the students or people who want to learn control systems, and it will incorporate many aspects of control systems, for example stochastic control, guidance, navigation and control. Non-linear control is already there. There are some lectures missing in the non-linear control playlist. I will try to complete that as well, and then I will try to start a new course, for example adaptive control or something like that. So I'll try to have some playlists of complete courses, and then there is another ongoing playlist regarding the research papers that will continue hopefully. So in this lecture we briefly revised how we convert state space transfer function and differential equations into each other. Then we looked at the motivation for linear approximation, and the motivation is that the linear approximation does work in real life. So that is a lot of motivation for us to learn linear approximation. So if we have a nonlinear system at hand, we can convert it into corresponding linear system and apply the linear control design tools on it, and apply that linear control on the original system, which is basically nonlinear. But if we confine ourselves within certain ranges, then we should be fine, and that is what is happening in real world right now. So this was the conceptual slide in which I just gave you the concept in one dimension, where we pick some point of interest and find the linear approximation by the slope of the function at the point of interest. And then we looked at some pendulum example. We did a linear approximation of that example using the equilibrium points and the approximation of the sine function with some geometry, and it was I hope that it was a little bit of a fun, but this control systems is only fun when you truly understand it. Before that it is a lot of pain, but no pain no gain. So that's fine with us. Some of us come into this world and we don't want easy life. We just don't settle for it. We want things that challenge us, and we like challenges, and we face them every day, and we feel good when we overcome the challenges. So step 1, step 2. Step 1 is to write the system in the state space form. Step 2 is to write the equilibrium point, to find the equilibrium point values. Step 3 is to find the Jacobian matrix, and step 4 is to evaluate the Jacobian at the equilibrium point values. Then the step 5 is to write the linear approximations in the matrix form. And then this was the summary of the 5 steps. And then we have the linear approximation with control. The only difference is that you have to define U star up front, and then you find the Jacobian and evaluate the Jacobian. So in the difference is that in this case there are 2 Jacobian matrices, one with respect to state and one with respect to control input, and you evaluate the Jacobians with respect to the equilibrium point values of state and control. You get A and B matrices of the linear approximation. And then we looked at another example of third order system. We converted it into state space. We found its equilibrium point, which was 1 0 0. We calculated the Jacobian matrices, and then we evaluated the Jacobians at the equilibrium point, and then we write down the final state space. So I hope that this lecture was useful for you. Thank you very much.